Okay, well, it's really an enormous pleasure for me to introduce an old friend, Yang Hui-He, who first visited, I think we met when he visited India in 2001, I believe, for
Yes.
the STRING conference,
Oh,
which are one of the organizers. Those were fun times. Maybe those were more fun times for string theory than they are now. I don't know, but they were very, very fun times, no question. And I caught up with Yang earlier this year when I gave some lectures at this London Institute of Mathematical Sciences, and he was a wonderful host. So Yang has worked extensively in string theory, in the interface between quantum fields and strings, and algebraic geometry, number theory, machine learning, artificial intelligence. And he just told us that he's an amateur at AI, but Wikipedia says he's one of the pioneers of the field of using AI for pure mathematics. So I'll leave the audience to decide whether he's a pioneer or an amateur or both. And with that, I'm greatly looking forward to this talk, the AI mathematician. Yang, please go ahead.
great. Thank you very much for this kind invitation. I'm very honored to speak in this great series because I'm a big fan of Harish Chandra, who is certainly one of the greatest, mathematical physicists in both directions of the 20th century. And I'm especially happy to see Sunil, who's been very kind to me since 2001 when I was still a PhD student when I visited India for the first time. So just a little bit before I start, I'm going to talk about some of the stuff I've been working on recently about how to use AI for discoveries in mathematics and theoretical physics. I'm a novice in AI in the sense that I don't really work in sort of the theory of AI. I really want to apply AI to try to find or accelerate discovery, if you wish. But just before I start, it's kind of very timely that I get this invitation because let me just tell you a little bit about the London Institute. So this is just the one slide. So we're, as Sunil said, we were very happy to have hosted him earlier this year. And this is the first independent institute in the UK for the mathematical sciences. So for fundamental blue sky research in the mathematical sciences, but we're very fortunate to be hosted by the Royal Institution, which is this ancient establishment since the 1799s. And one of our 23 themes is AI for mathematical discovery. So with 23 is appropriately chosen because of Hilbert's 23 problems. And in 2022, we established the Arnold Orlando fellowships. And the reason I say this invitation to speak here is especially timely because we're just in the process of establishing the LIMS India Fellowship as supported by the Indian High Commission to the UK. And then this is very timely. I hope this works out and LIMS and India can become good friends. So there will be many, many more exchanges. So back to this, to the topic. I know this is a series on arithmetic geometry and theoretical physics, and I will certainly touch upon some of that. But let me just begin with a little bit broader view of what I've been thinking about in the past 7 or 8 years. And really, it begs the question of how does one actually do mathematics? I would like to think of mathematics as sort of a three-way thing, sort of 3 ways to do mathematics. You can think about mathematics as a bottom-up approach, as a formal logical system. I'm borrowing these words from theoretical physics, of course, because I think these words mean different things in philosophy. You can think about mathematics as a top-down, as a creative, intuitive art. And you can think about mathematics as a language, in what I prefer to call as a meta-mathematics, in this era of meta science. And I try to review some of this in this recent, actually just a couple of weeks ago on this Nature review on how this is. So a lot of the talk is based on this particular review. And there's an early review of how one can use machine learning to study the structure of mathematics back in a few years ago. So needless to say, the 20th century, computers have become increasingly indispensable to mathematics, to mathematical research in general. But perhaps what is less appreciated are the fact that there are foundational results in mathematics and theoretical physics. I'm going to use mathematics in the British sense. That includes, from now on, that includes theoretical physics, so I won't have to say it all the time. So some foundational results, like the four-color theorem, the Kepler conjecture, are just, one cannot do them now without the help of computers. For example, the Kepler conjecture, this is stacking of spheres in 3 dimensions, has only been done, 400 to 500 years after Kepler, and by reducing it to a case-by-case check on computer. And it's the same as four-color theorem. The really interesting one that I would like to see at some point that would have to be done is the classification of finite simple groups, which took almost 200 years to complete the proof. And the most important fact, as I hear from my expert friends in this area, is that no single human being has actually read the entire proof. And it is absolutely not possible anymore to read this entire proof, because it'll take longer than the lifetime of any expert to read this. So this has to be computerized at some level. So let me just begin a little bit. I won't say, the point of this talk is that I won't say too much about bottom-up, and I won't say too much about meta, and I'll explain why. And I would like to say, my point of argument is that we're really, one of the more recent breakthroughs that is more, in the last 5 years, has been this top-down approach to mathematical discovery. So let me just begin with, what mathematics is from a bottom-up approach. I mean, this really started by this Russell and Whitehead's Principia Mathematica in the early 20th century. And of course, one could argue that this is a program that goes back to Frege or Leibniz or even to Euclid to just axiomatize what mathematics is. This entire program of writing down sentence by sentence mathematics was completely killed within 20 years, because Gödel and Church and Turing proved the undecidability, the incompleteness theorems. They are, within each order of logic, there are statements which is undecidable. But I love this wonderful quote by my friend and colleague, Professor Min-Young Kim. He says, the practicing mathematician does not worry about Gödel. If you spend your every day worry about whether your equation is derivable or whether your theorem is provable, then you essentially, you won't work anymore. The space of provable statements is so vast and so interesting. We can park for now the undecidable problems. And this is not just, oh, has it stopped? Okay, no, it's okay. I'm okay.
Sorry, no. So the recording, I don't know who did that, but whoever's started it should please restart it, I guess. Let's just give a second. Who is the host? Let me just see.
Yeah, just
Julie.
wait for 2 or 3 minutes. We'll let you know once it starts.
Okay.
Yeah.
So sorry, you have to just
so
wait.
I pause?
Yeah, please.
Okay, that's no problem. Yeah.
Sorry about that. This was going
so we can
great.
muse a little more about philosophy.
Yeah. It's really getting interesting now. So yeah, maybe I can just ask a question in the meanwhile. So Leibniz was sort of, you say even Leibniz, was that the oldest person to talk about axiomatizing mathematics as in the language we use today?
Yeah, so this is something I learned more recently with this visit to Hanover, whereas there is this, essentially the University of Hanover is this great shrine to Leibniz, because he was, and in fact, the University of Hanover has been renamed the Leibniz University of Hanover. And his whole basement when Leibniz had his calculating machine, he was thinking in binary. He was essentially thinking about formalizing mathematics in binary code. It was very, very ahead of his time.
Amazing. Okay, you can continue now. I think.
Continue. Yeah. So the practicing mathematician hardly ever worries about Gödel. It's not just a philosophical statement, but it's really, really interesting because it's essentially started with what's known as the ATP program. This automated theorem-proving program, which started really in 1956. Because these guys were able to devise a very, very early version of the computer. and they were able to prove subsets of Principia Mathematica. So that's kind of interesting. They were able to enter the sentences into this early computer. So that's kind of interesting. And then this thing really took off in 1956, and in stuff that I have no idea about, this tight theoretic language. And what's interesting is that this 1956-57 was exactly the same time that the first neural networks were developed completely independently. So they were thinking about kind of two different strings of problems, and yet it was so 56, 57 were quite magical times. So this ATP program now has become very much an active field of research. So one of the champions of this is Terence Tao, who's given many, many beautiful talks online. You can check them. About how mathematics has reached the stage where you need proof assistance to just formalize mathematics and go through them. So there are a lot of very nice programs, so you can they're freely available. The COC system and the Lean system, and Davenport and Buzzard have both given ICM addresses in 2018, 2022. The fact this of computer-assisted proofs really shows that mathematicians are really interested in this direction. And the Xena project I have to mention is the project where spearheaded by Kevin Buzzard in Imperial, which is to use the Lean computer type theoretic language to actually formalize all of undergraduate mathematics. And that's now, as far as I know, complete. So it's millions of lines of code, but now they have MathLib has all of undergraduate level mathematics. Of course, it's a tiny sector of percentage of all of research mathematics, but it's a good start. And now they have at least checked that undergraduate mathematics is self-consistent, which is great. So we have not been told lies so far.
I think there is some contribution of Vovodesky in this area.
I'm sorry?
There is some contribution by Vovodesky in this area.
Yeah, so Voivodsky apparently before the last year of his life, he spent his thing in what he called the homotopy type theoretic language. Okay. So, which is apparently a new efficient way of grouping these statements of logic. I'm not sure that Lean is actually implemented in this language because Lean predated Voivodsky. So it's still this type theoretic language. I mean, somebody needs to write a software to do this Voivodsky language, which is supposed to be better.
Okay, fine.
So what's interesting is that DeepMind, of course, they have a product to sell. They have very, very optimistic estimates. They say, humans beat computers in 90s, computers beat humans in the 90s and Go in 2018. So naturally, they should beat humans by 2030, improving theorems. This, I have no idea how you extract this from two data points. But obviously, it's I think Buzzard and Davenport both think that this is a very optimistic estimate. But it's okay. I mean, but we're inching towards that direction, and that's the important thing, as you can hear from Terence Tao's lectures.
So just to understand the statement that the Lean all undergrad mathematics has been meaning what that those are also there in the book. Sorry, I'm unable to understand what is the meaning of that statement.
Yeah, sorry. What I mean is that the Xena project has large parallel clusters of undergraduates and PhD students, and they literally got hundreds of people typing into the computer all of this, every single step of every single proof of undergraduate level mathematics that's taught at Imperial. So it's a very good benchmark.
I see, so, but right now it's just a typing, right? No AI
or typing, nothing generated, nothing generated. Okay. But at least it's nicer that you have this there's a math library called MathLib, freely online in Lean, and you can extract it's quite convoluted, it's not really human readable. But at least that has every single intermediate step of all of this level, undergraduate level mathematics. It's kind of very interesting. So that's all I'm going to say about bottom up. And I'm just want to
emphasize. I'm sorry to interrupt. But what is Lean? I'm not sure with the Lean term that you're using.
This is an extremely good question because I don't know what Lean stands for either. I've been Googling, so I don't know why it's even called Lean. But if you type Lean math software or Lean MathLib in Google, you will find it's all free and it's all interactive. It's called an interactive proof assistant. And I highly encourage, I played around a little bit with it, but it's basically a good way to formalize mathematics. It's basically the 21st century version of Principia Mathematica. So I think that's a good way of putting it, because it's all in the computer. Hundreds of thousands of lines of code, and people contribute. It's a big community now contributing to this. Right. So that's what I'm going to say about this bottom up. And I just want to say that this ATP program really has been around for 70 plus years, and it's still going very strong, and it's definitely going in this right direction. So the next thing I'm going to say is this meta mathematics, mathematics as a language. And this is essentially what I mean by this is ChatGPT plus. We know in 2022, ChatGPT has passed the Turing test. This is somehow not all over the newspapers, but it should be. It's on some newspapers. If you talk to a ChatGPT, you can't distinguish whether you're talking to a person or not anymore. So it's natural. I won't get into the details of some early experiments that's been done of just taking mathematics. I'll probably talk a little bit more of this early experiment that I tried with his friends about just machine learning the archive. But the point is, ChatGPT is beginning to process mathematics as a language without any understanding what mathematics is. But so that's level one. But the next level, which is very interesting, is that it's the large language model for mathematics is now very much in the air. So you can see where this is going, right? You take the entire proof of Lean, millions of lines of code, machine learn that by large language model, and then try to see whether you can generate new mathematics. This is essentially being done by Meta's Llama and OpenAI's QStar, which should appear. And earlier this month, actually, DeepMind announced AlphaGeo and AlphaGeo 2, which are large language model processors for Olympiad level math. And AlphaGeo is at 53%, and AlphaGeo 2 is now at 84%, just as of earlier this month. So they can. What I mean by that is that you give a problem in Euclidean geometry. And the AlphaGeo 2 DeepMind can scan that problem and generate a proof that's human readable. It's a bit convoluted, and 84% is 84% correct. So it's good enough to win the silver medal. Once he gets a gold medal, and that pretty much obviates in some sense Math Olympiad. But of course, this is only for Euclidean geometry type of problem, because their training set was just on Euclidean geometry, which are hard. These are very, very difficult, tricks you have to use. But they can do it now to 84%, which is kind of impressive. So, but the one that I really want to emphasize in this talk is top-down mathematics, which I think is taken off much more seriously in the last few years. And that is really, in a way, how do you imitate research mathematics, right? So I've talked about, building up mathematics from foundation. We've talked about mathematics without any understanding of mathematics. But then you're like, what do we do all day? We as mathematicians and theoretical physicists, a lot of it is really dependent on intuition, experiencing, and experimentation, right? So we are the countless examples by this. If calculus had to wait for formalization and analysis, we wouldn't even have Newton's laws. We just have some kind of a fuzzy idea of what needs to be done. And I'm trying to argue that this fuzziness is actually extremely adaptable from research there's a whole area of AI very much adapted to this kind of fuzziness. So just to give you an idea what I mean by this, I also asked this question, what was the best neural network of the 18th and 19th century? Well, that's clearly the brain of Gauss. That's indisputable that this was a neural network that was better than any other neural network at this time. And what did this neural network do, right? It was able to just look at graphs like this. Mind you, the Gauss had a plot. So this is a plot of the number of primes less than or equal to a given real positive number x. So this is what with the prime counting number, the prime counting function. Gauss was able to calculate this, and he had tables up to tens of thousands, but then he had to calculate even further by hand into the 100,000 range of primes, and he even made mistakes. But then was able to plot this and look at it and says, well, this is clearly x over log x. That's quite impressive, right? And just, how did he know this? What made him think to do something like this, right? And this is 50 years before Hadamard and Delavoye-Sans proved that this is true. And this proof relied on complex analysis, which needed Cauchy and Riemann, which came after Gauss, to be able to settle this proof. So it's kind of interesting that Gauss was able to conjecture something like this before the invention of the technique was even ready. And something else was like this famous, of course, this is a Millennium Prize problem of the Birch-Swinnerton-Dyer conjecture. And what these guys did, well, they went to the basement in Cambridge and then plotted ranks and conductors of elliptic curves, and were able to make a conjecture which is still open. It's worth $1 million, and why were they doing this, right? So I love this quote. I don't think Sunil has seen this. I've shown this before, and I'm a big fan of this quote. This experimental mathematics is a very ancient subject, contrary to what you might think. Even before the age of computers, because Gauss was just mucking about, at the age of 16, computing primes in the tens of thousands, and to establish this plot, because he wanted to know, and then he was able to spot it immediately, and then in the age of computer, Birch-Swinnerton-Dyer was able to make were able to make the conjectures. So let's do an experiment of what experimental mathematics is. So if I gave you this sequence, I think you can pretty immediately tell me what the next number is, right? And the next number this is just whether something's a multiple of 3. The sequence of integers of a multiple of 3 not. If I gave you this one, you might struggle a bit, but then if you spend maybe like 10 minutes doodling about it, you can probably guess that this is prime or not, the prime Q test to integers. Obviously, the evens I don't need to check because they're all 0. This one, you're going to have to probably, struggle a little bit. And what I've done here is just the sequence of the parity up to multiplicity of the number of prime factors. This is a shifted version of what's known as the Liouville lambda function. So 1 second for the human eye, 10 minutes. And this one, I think, it's a bit hard. Unless you're biased, somebody told you it comes from number theory, probably it's hard to guess. So experimental mathematics in this sense, and in the age of AI, is basically, can AI spot patterns from something like this? And that, after all, to quote the great Hardy.
Sorry, can I just ask one thing?
Yes, of course, yeah.
Slide, I'm sorry, I missed, what's the point of the previous slide? Sorry, it just 0, 1, 0. Can you please repeat the point? I missed.
Yeah, sorry, yeah. So in this sequence, the human eye can probably tell the next one is 0. Now, what is the next number in the sequence?
I see.
So this one, once you recognize what the pattern is, there is this. So we're essentially formulating conjectures, right? Mathematical data is a kind of interesting data, right? There's no error, there's no variance. There's just absolute, the next number is either 0 or 1. There's no other possibility to this. Right. So that's what I want to emphasize.
Okay.
So, and I'm saying that essentially, Hardy defines what we do. Mathematician, of course, includes theoretical physicists as well. We are makers and detectors of patterns. And if there's one thing that AI can do better than humans, is pattern detection. And so this is what got me thinking about this, about 7 years ago, right? And so let's do this experiment. Of course, if I blind, I mean, there is a thing in Mathematica even called sequence predict. So if you put this into sequence predict, it will give you 0. If you put this one, it's a bit harder. And in fact, sequence prediction is quite difficult because it doesn't, the feature space dimension is not large. So it's very hard to to do this. So let's try to do some feature engineering. This is what I'm giving you buzzwords. Feature engineering to turn this into a very adaptive AI problem or machine learning problem. So one thing I can do is to take a sliding window, say of length 100 on my sequence of binary. Obviously, I've chosen this to be binary, to be standardized. But then again, you can say that any problem in theory is a binary sequence, right? That includes all problems. So you do a sliding window of say length 100, and then I'm going to label this to be 1, to be the next one outside the window, and I'm going to slide this window to predict. The reason I do this is to just add dimensionality and add feature space, to add features. So now in machine learning, this is known as a binary classification problem of binary vectors, right? So what I can do is I can take 100,000 of this. It's cheap. Arnold had this great quote, mathematics is a branch of physics in which data is cheap. Well said, right? And in general, especially today, you can just do this. You can generate 10,000 cases on a computer in less than a minute of this. And you take training set, and then you just validate it. Can we use some standard algorithm to do this prediction? And there are many standard classifiers. There's some things that there are support vector machines, there are base classifiers, nearest neighbor. All these buzzwords you learn from this machine learning 101. As I did. I mean, I took machine learning 101 by looking at internet videos. As how, this is how people learn things these days. And as I will revisit Sunil's wonderful lectures in quantum field theory by learning them on video. That's how people learn these days. So you can take, the buzzword is called, the jargon is called cross-validation, what that means, you take your sample, say 50,000 samples of this.
I have a question here.
Yeah.
So like it has been quite a while for me when I started actually learning maths on this front. But then can we say that we have artificial intelligence in picture from those decades wherein these theories came in picture? And artificial intelligence is like not a new thing which we are seeing in the recent past. So we have these algorithms, these predictive models already being in existence for a long time. And AI is really there with us in this form for quite a long time in the past.
Yes. You're absolutely right. In fact, these nearest neighbor classifiers and base spectrum have existed since the 60s. So the game changer is the GPU. So I think why has AI become such a big thing? Everything is just compute. Why has it been a sort of a revolution in the last 10 years? Is because your laptop now has GPUs. So essentially, your laptop now can train neural networks, which could only been done on supercomputers before. And this is now suddenly AI is to the masses. And that's why it's like if it's something's at your fingertips like this, these are, you're absolutely right. These are all ancient techniques. The neural networks that go back to, theory of neural networks, 1957. And so, but what is the game changer is that any person can extract freely available data and then train it on your laptop very quickly. And that changes everything. So
exactly.
Sorry?
Exactly. And we basically say a random example is we basically used to have a tool called as say resharper in .NET programming. So it does the same thing. Like we are predicting numbers here and the series. It tries to predict the code in a better style against the one which you have written. So in a way, it was kind of a predictive analysis or predictive maintenance for your programming also. So I just want to understand that how came this AI burst suddenly started booming in? Because this thing is so, we have this thing for quite a while in the past.
Abhijit, sorry to interrupt. I think let's keep our questions brief. So, because otherwise, we have limited time for the talk.
Oh, we
so
do. We do have limited time?
I mean, not
Okay.
in principle, that's strictly limited, but it's good to keep the long questions maybe for a discussion at the end, towards the end of the talk. Is that okay?
Sure. Yeah. Yeah.
Thanks. Yeah.
Sure.
I will
Okay,
get back.
thanks.
I'll get back to that comment, but just in brief, is that you have at your finger. I mean, the basic short answer is that you have your at your fingertips the ability to train deep neural networks on your laptop, and that's a little more sophisticated, which could not have been done 10 years ago, and that's a bit of a change. Anyhow, so back to this thing, which if you train on any of these things, you will get. So what I'm recording here is accuracy and also precision. So precision is a percentage correct, and I'm also going to record essentially the chi-square just to make sure as a double check. So for the mod3 problems, any of these algorithms is going to give you 100% accuracy very quickly. It better, because this is a linear transformation. The prime Q I tried is 80%. I don't know why it's 80. It's kind of you can imagine it's doing some kind of a seed method. What's really interesting is that this problem, this Liouville problem, I couldn't find anything that breaks even. 50% is coin toss, and is essentially zero chi-square. And that is very, very important, because I'm not saying it's impossible, but the point is, if you can break even, if you can do better than 0.5%, you have a very good shot at proving the Riemann hypothesis, because the Riemann hypothesis is equivalent to the ability to predict the next number in this sequence. And in addition to the Riemann hypothesis, you will also break every single bank in the world, because you will have a grasp to its prime factorization that nobody else has. It's disappointing and reassuring that I could not find a neural network that breaks even from a theoretical point of view. So, so back to a little bit more on this. How do we, as Sunil said, my background is in string compactifications and in using algebraic geometry. So the first problem that I thought about doing was this following problem, which is to compute Hodge numbers of Calabi-Yau manifolds. So that's something that was sort of my bread and butter that I grew up with. The point is, a Calabi-Yau manifold, like any other algebraic variety, can be represented as a matrix. Because so I'm just recording multi-degree embedded in product of projective space. And this is a general statement. Any algebraic variety, in fact, any manifold that's representable as algebraic, can be written down as some kind of a matrix representation in sufficiently large embedding. And then the point is that, then Bourbaki tells us you got to chase sequences until your face is purple to produce a number like 22. It just says the Hodge number of this is 22. And the 22 has meaning in string compactification. But then I got thinking, well, what I was thinking back in 2017, very naively, was like, how different is this from an integer digit recognition problem, right? You can always represent a tensor or a matrix as a picture, and then the fact that this picture is to be labeled 22 is just a digit recognition problem. So in machine learning, the ultimate example, it's like, you take an image, you vectorize it or you tensorize it, and then you try to say that this is the number 5, and you need a lot of labeling. And then the point is, I won't bore you with all the details. The point is that this is a digit recognition problem. You can train some generic neural network to see, say, 20,000 cases of stuff like this, and then start predicting. What I was completely surprised by was that it was actually doing fairly well. This has been recently improved by Finatello and lots of people that to 99.9 plus accuracy, that you can just look at the picture and then say what his Hodge number is, just because it's learning some secret formula that we don't know about. So I went, and then it became a fanatic, like a new convert, you become a fanatic. So I become a fanatic. So I've said things like, well, algebraic geometry is an image processing problem. In fact, computable mathematics is an image processing problem. And I've said this in front of like algebraic geometers, and I haven't been shot yet. So I think at some level, there's some truth in this vast generalization of a statement. But it is in some sense true that computable mathematics is just image processing. There's some secret formula underneath that's giving you what computability is. So then, since then, I've had the pleasure of working with many. I've learned so much from both my students and my collaborators on just give me your favorite data. So for this audience, you were particularly interested in representation theory and maybe algebraic geometry and theoretical physics. Just give me some representable data and let me try to give you let me try to train a neural network that will predict it correctly. And I'm going to address this issue later about, is this useful? Well, it's useful computationally because if you're computing things like string landscape, this is going to speed up if you want to just back an estimate, it's going to speed up many orders of magnitude. So for example, in this work with Overett and Ashmore, we were able to, this back in the day, we were looking at the Donaldson algorithm of generating metrics, numerical metrics. And then we just looked at it without understanding this algorithm, just looking at the data it generated. And then it started to perform to a reasonable accuracy, almost 2 orders of magnitude faster than the Donaldson algorithm, which is a well-established algorithm for numerical metrics. That's obviously useful if you want to do string, if you want to compute the mass of an electron from string classification, that's useful. So that's now been improved by Laura Anderson and friends and Michael Douglas and Fabi Rula and Jim Halverson. They've specialized neural networks that just pinpoint the fast calculations of numerical metrics. So that's obviously a very important thing for theoretical physics. Oh, by the way, buy these books. So I get royalties. This is a shameless self-advertisement of books. I get £5 a year, so I don't have to sell my liver for my children's education. But more seriously, so this goes back to this another more serious point. It's like, oh, fine. So you've got this neural network that does this thing, and pretty much reasonable mathematical data, because they're structured, you're going to find some neural network that will outperform regular algorithms, because that's just the way things are designed, because of nature of mathematics in some sense. Of course, I'm neglecting everything that's not mathematically computable, right? So then, but how is this good for actual discovery, right? So last year we were in half year. I organized this conference in Cambridge with Nampuri and Domelo Koch and friends, and Cardoso, on just having a dialogue between various people. And this is sort of in response to the ChatGPT passing the Turing test in 2022. We try to say, well, let's try to have something that's a little more rigorous, in the sense of how do you have a Turing plus test for AI-assisted discovery in mathematics? So, and I think in some sense, we reported this very briefly in this correspondence with my friend here, Burtsev, he really is an AI expert. That's his Misha Burtsev, who is he's our AI fellow. And so we tried to formulate this and name this after Birch, inspired by this talk by Birch. Birch, who is, by the way, he's still around, and he's in his 90, and he's still very sharp. And to just go the next level beyond Turing, ChatGPT past Turing. So if you have a discovery of this thought, if you put in some neural network that does some kind of prediction correctly, so interestingly, we formulated this test in a way that's AI plus N, but AI stands for something else. So first of all, it has to be, A stands for automaticity, in the sense that your mathematical discovery, if you predict a conjecture in mathematics, and that's to be conjectured by AI, it must be entirely generated by AI. You can't be like some human intervention at every step, because of your bias in the system. Here's the crucial one, is the I is for interpretability. This is the biggest challenge right now to black box methods in artificial intelligence. If you're a doctor working for, say, tumor diagnosis, and your AI system, your deep neural network is diagnosing tumors from scans. That's great. That's good enough. Because in some sense, we don't. If your AI system is outperforming humans, it's great, right? And in fact, NHS is already. My friends at hospitals, they're already saying some extreme things, like they're no longer training the next generation of eye doctors, because no human doctor already at this year no human doctor can diagnose eye disease better than AI system now, because AI system has the entire database of all previous diagnosed cases. So a diseased eye, you should trust an AI diagnosis more than a human diagnosis now. But for us, theorists and mathematicians, that's not good enough, right? We want to, a black box is useless. Even if it does 99% accuracy, 99.99 accuracy, we want to know what is actually doing, what is the underlying theory. So that's the I for the AI. And N is non-triviality. If you conjecture, we're now at the stage where AI systems can conjecture mathematics very, very efficiently. In fact, it can pump out millions of conjectures a minute. But how many of them are actually interesting? This we don't know. And how many of them are actually non-trivial? So it has to be non-trivial for people to work on it. So that's another challenge. And most importantly, this AI plus N test has to make Birch happy. So when is he happy? Oh, no. So far, he's not happy. So far, all of these AI conjectures, including some of my own, has not made him really happy. So just to give you a couple of examples, for example, this Calabi-Hodge computation, it fails the eye test. Some deep neural network, it's great, yeah, but how is it helping us? How is it making us understand the nature of exact sequences or the nature of algebraic geometry? We don't know. Similarly with this, I won't bore you with this representation of groups. So since this is a representation theory talk, here's a very interesting one. We're able to do this with Min-Young Kim. If you take the Cayley table of finite groups, so every finite group is uniquely determined by its multiplication table. It's an n by n table, which happens to be a Latin square. And then there's some permutation of that. So we were able to do, we took about, I think, 20,000 such Cayley tables, up to permutation, and label some of them as simple groups and some of them as non-simple groups. This is a crucial point in finite group representation theory. We're very surprised that if we plotted this in an n squared dimensional space, there's a separation hypersurface that takes simple groups from non-simple groups. Don't know why. I mean, this is almost interpretable because I'm telling you what the hypersurface is, but the hypersurface changes as you include more data. So it's not, yeah, but it's a very strange way to do representation theory. And I've told many people so I'm hoping this crowd, or since Harish Chandra is a great representation theorist, I hope his ghost can inspire us to actually inch out some conjecture out of this, but I don't know so far. And even so, I won't bore you with this one. So there's this beautiful paper in 2022 by DeepMind and collaboration, Jody Williamson, and they were able to get new knot invariants by looking at Jones polynomials of knots, large classes, I think something like 3 million. And this one passed actually the A test and the I test. So it's interpretable. They were able to get an actual conjecture, and they were able to get a automated conjecture formulation by so-called saliency tests of their data. But it still doesn't make Birch happy because it doesn't pass the N test. This conjecture that was raised from this paper in 2022 was not non-trivial enough. They were able to settle their own conjecture within a few months' time. And the list goes on. There's this nice paper of Veneziano, predicting quantum periods. I'm just giving you a sample of just sort of the progresses in the last 7 years. I mean, there are hundreds of papers now on machine learning mathematical structure. It's hard to, so I try to include it as a complete a review as possible in this Nature review that I mentioned earlier in the slides. And so there, even this one, so we were able to find a new Calabi-Yau fourfold by using a genetic algorithm, being just in this genetic algorithm search, which I guess genetic algorithm now goes under the rubric of AI. But as mentioned earlier, genetic algorithms have been existing since the 1970s. But now we have the compute power to actually make this doable. Again, this fails the N test because it wasn't non-trivial. Sure, we generated a new Calabi-Yau fourfold, but so what? There are many, many more one can generate. But just to wrap up, since this is a talk on arithmetic geometry and representation theory and theoretical physics, you may be rest assured that that's something that's almost made Birch happy, is the so-called memorization conjecture. This has passed the I test and the N test, but ironically, it failed the A test. So it's non-trivial, it's interpretable, but it wasn't entirely generated by AI. And I'm going to give it a little bit, just in sort of in 5 minutes or so, to tell you about what the memorization conjecture is. And it comes from arithmetic geometry, and why this passed I and N and failed A. So as I mentioned, experiments in number theory could get very, very hairy, because, once prime numbers are involved, you're going to, very quickly run into problems that are equivalent to Riemann hypothesis. I was very happy to find that, this experiment, this very baby and naive experiment that I was mentioning to you earlier, this sequence that I want you to eyeball, the great Peter Sarnak, which was one of the world leaders in analytic number theory, gave this to Google DeepMind independently in the 2020, in the early, say 2021, 22. And he gave that sequence to DeepMind and said, find the next one. Can you devise some kind of a clever trick? Because Sarnak's, obviously, he's heavily invested in this, because he spent his entire career thinking about the distributions of the primes in this consequence. And he's deeply, and I've learned from him that, that this problem has incredible implications towards the Riemann hypothesis. So DeepMind wasn't able to break even either. So fine, okay. So my baby desktop and baby, machine learning 101 algorithms were not doing any worse than DeepMind's super power. But I challenge anyone to do this. But Sarnak challenges anyone to find a pattern in this. So then I got thinking about back in 2019 with data scientists Baron Kelly and Andreetti. Well, it's a nice way to can machine learning say something about the BSD conjecture? The reason I chose the BSD conjecture instead of the Riemann hypothesis is because the Riemann hypothesis again doesn't have enough features. The feature space to the Riemann hypothesis, the brute force way, is very, very small because it's just the plot of zeros. It's very hard to say, well, is the next zero going to lie on this line or not? Whereas the BSD it has many, many more things. There are elliptic curves involved, there are L functions. So you can engineer your data in a much more serious way. So that's what led to this memorization conjecture. And I'm going to, just stare at this picture. Probably my biggest contribution to this collaboration with Kyuhwan Lee, Tom Oliver, and Alexei Postnikov. So these are card-carrying number theorists. Was to insist, my biggest contribution to this project, to insist that the paper be called the memorization conjecture, because it reminded us of the flock of starlings. So just very briefly, what the conjecture is. So very, very quickly. So if I give you an elliptic curve, well, first of all, one slide on what the BSD conjecture is. If I gave you an elliptic curve, and this is something we're all familiar with, physicists to string theorists to geometers to analytic number theorists are all familiar with elliptic curves. But the point is, if I give you a cubic polynomial in two variables, how do you find all rational points on this? That's a very, very hard problem that goes back to essentially to Diophantus. But a lot of the deep developments of the early 20th century is to realize one way towards this problem is to create the generating function. So instead of how do you find Q points on the elliptic curve? Well, you don't work over Q, you work over finite fields, FP, and then literally count the number of points. Because it's a finite field, you can do this exhaustively. Just check, grid search. And then you formulate this generating function. The fact that this generating function takes a rational function form, a polynomial over polynomial form, is the deep result of they, and which was settled by Deligne and Grothendieck. So long story short, if you write down this function, the thing that captures is this deviation from the number of primes of your finite field. So the number of points. So this is what's known as the Euler coefficients. They're called Euler coefficients because they have multiplicative properties. This is something that Ramanujan would appreciate very much. So long story short is if you take the product over all the numerator, and call this the L function, the BSD conjecture essentially says, so this is the strong version, but the weak version of the BSD conjecture says that this function knows about the rank of the elliptic curve, or the degree of infiniteness of how many infinite families of Q solutions, rational solutions are there of your rational points on your elliptic curve. So that's, if you solve that problem, in fact, it's even more precise. The order of vanishing of this function, the L function, the global L function, is the rank of elliptic curve. You solve that, you get $1 million and you become immortal. So this is still open since the 1950s. So what I was doing earlier with these guys who were data science, because we're not experts, right? So I took the Weierstrass representation of the elliptic curve to just predict the rank of the elliptic curve. And I got terrible results. It's essentially random guess. But then I talked to these number theorists, these card-carrying number theorists, and all of a sudden, by using these AP coefficients to predict, and again, the feature space is good. You take the first n of these AP coefficients, where n is a sufficiently large prime number. Sufficient large here means 20 to 50. It's not like 20 million. Just take the first 20 primes and work over F2, F3, F5, F7, these finite fields, reduce elliptic curve of this, and count the number of points there are. So that's a vector. So there are deep theorems of Grothendieck and Deligne and Dwork that says that the growth rate of these numbers is just at most square root of p. So you can normalize by square root of 2 p, and then you can become a fairly standardized vector. Now you take these vectors and you say, well, what is the rank of the elliptic curve? Just do this prediction, sequence prediction. And suddenly it becomes like 99% accurate. And I said, oh, that really is really good. You've improved a nonsense prediction to an almost 100% prediction. And then, my distinguished number theorist colleagues, Lee, Oliver, and Postnikov, and they tell me, well, the Postnikov was involved. Lee and Oliver says, of course this is true, because BSD tells us that this should be true. What is deep about the BSD conjecture is that there is no known analytic formula of the rank in terms of the AP coefficients. Everybody knows there exists a formula, but nobody knows what it is. Whatever it is so complicated because it involves all these products over all these things. It's very, very hard to write it down. So the neural network has found a way to predict it using some convoluted formula that can't be even interpretable. So that in itself is not interesting. It's remarkable because the neural network doesn't know any mathematics at all. And yet it was just by pattern recognition able to predict the right rank 99.99% of the time, which is, over 3 million cases is quite impressive. But it hints towards the BSD telling us something is deep. So we did something else. We tried to make it interpretable, right? So so far there is AIN are all failed in this experiment. It's neither automated, nor interpretable, nor non-trivial. So far it just says the neural network hints towards something deep about the BSD conjecture. So then we did something totally stupid. It's known as a PCA, or principal component analysis. This is like apparently statistics 101 or AI 101. If you open up any AI book, this is like chapter 1. So PCA, what a principal component analysis does is takes a high dimensional data, it projects to a lower dimension of your choice, say 2 dimensions, and by picking out the direction that has the biggest variance, that's the principal component. It basically looks for the direction of the biggest or the dominating eigenvalue in the big matrix of projection. Right. So that's a standard statistic trick. And then what we did is to label 0, 1, and 2, the ranks of the elliptic curve. So by the way, there's the theorem of Manju Bhargava, he got the Fields Medal for this, is to prove that 50% in the infinite limit, 50% of all elliptic curves is rank 0, and 50% is rank 1. So it's a very deep result. But of course, there are others. I mean, there's 0, 1, 2, all the way up to number 28. And we don't even know whether the rank goes up to infinity. It's just that statistically it's 50-50. But in the million range, you still see there's a significant percentage which is rank 2. So this is why there are 3 blobs. So we did this projection because the neural network has hinted us that we should, there's something underlying. Can we make it interpretable? So we did this prediction, and wow, all of a sudden the rank 0, rank 1, and rank 2 elliptic curves separated. Right? In the 20, I say you take the first 50 primes, in this 50-dimensional data reduced to two dimensions. And then, okay, fine. And then Pozniakov, who was just a remarkable undergraduate student of Lee, we know because he's a Python god. He eats 20,000 code of Python for breakfast every day. So we made him look at the actual matrix transformation. So PCA is great because it's a linear transformation from dimension 50 to dimension 2. So he looked at these and he saw that they're all focused on one column. So they're mostly just focused, all the others are just fluctuations. So what does that mean? It means that because this is a prediction, it's a linear transformation, if your PCA transformation is just focused on one column, it's just doing an average. Right? So we're very happy that Pozniakov will start in September to be Peter Sarnak's PhD student at Princeton. So this is great. He had a stellar career even as an undergraduate student. So this average process, I won't bore you with the details, is now known as a vertical average. It's something you wouldn't think to do. The AI has told us to do the right average. This is an average over different elliptic curves, but at fixed prime. Normally, you would average over different primes for a given elliptic curve. But because we did a PCA, it tells us to average different elliptic curves for different prime, for fixed prime. And then you can plot against primes. And then all of a sudden, you see that this averaging produces this very memoration-like pattern. This is like a memoration. And so the conjecture is very now we passed the I test because this is not interpretable. You take this theorem. At the time, this all was trivial. So we wrote to Sutherland and Peter Sarnak and say, is this known? Is this averaging known? And we're very surprised to say that Sarnak wrote back and says, no, this is not known. And so now, so this is conjecture. You take this average and you can make more statement. This is to appear with Sutherland. Is that there's scaling invariance in this as well, but I won't bore you with the details in Europe at the time. And the point is, here's a conjecture, do this, and the idea of the memoration conjecture is that the distribution over elliptic curves should give you this, and it should disappear in the infinite limit. The memoration should converge to an exact curve, an oscillatory curve, and how it oscillates will tell you exactly what the rank is, and that's kind of interesting. If it oscillates in the blue way, that's rank 0. If it oscillates in the red way, that's rank 1. And then, in fact, this should hold for all L functions, and in fact for modular forms. So if you can take any arithmetic problems, this memoration should be a universal problem, and it should be a universally scale invariant phenomenon. This is now proved as a theorem for Dirichlet characters by my friends in 2023, and Lina Zubrilina and Alex Cohen proved it also for weight 2 modular forms. But the general statement is still open. So this is why I passed the I and the N test of the Birch test. It's non-trivial because people are still working on it. It's interpretable, but ironically, it failed the A test because we told the AI system to look at PCA but we mucked around. It's not like we threw this 3.5 million elliptic curves and the AI was told us automatically that we should look at this. That would be great. That's obviously the next stage. But I think in the near future, this is going to be the next step, where conjectures will be auto-generated. And then we have some kind of a verifier to pick out interesting conjectures.
Sorry,
so let me just finish. Yeah.
Just a quick question. So if you could go back to these these graphs of yours, The previous slide, I think.
Yeah.
Yeah. So this is what you mean by murmuration, right? It's some density of points in a band.
Yes.
And what can you just say what is exactly clustering in this band? So what are the axes?
Yeah, sorry. Yeah. So as I said, so you plot against the prime. So that was the thing. You average different elliptic curves given a conductor range. So you fix a conductor range, and then you average different elliptic curves and plot the rank of the you plot this average over the elliptic curves as a function of the nth prime.
Okay. And R here is the rank?
Yeah, R here is the rank, exactly. So for different R, the behavior of this average would be different.
I see. And what is the information we get from this graph? I see that there are two bands, one for rank 0 and one for rank 1.
Yeah, so the red, I believe, if I remember, so the red one is for rank 1 and blue one is for rank 0. So they oscillate differently. And in the bottom, you see we group because they're also even because then in the asymptotic limit, it's only 0 and 1 rank. But for any finite distance, you're going to find 0, 1, 2, 3. So we then grouped by even rank versus odd rank. And here's a plot of all the let's see the F0 and F2. So they're all this is a even rank and this is also even rank. So they oscillate the same way.
Okay.
So now you can prove that this. So the remarkable thing about what Zubrilina's proof is that she actually found proved rigorously as n approaches infinity what this murmuration should converge to. And it's not an obvious curve at all. It's some, piecewise arctangent curve.
I see.
So that's why you wouldn't have it's a bit bizarre. And I'm not enough an expert in number theory to tell you that the shape of that precise curve has apparently deep implications to the study of L functions. It was an unexpected result of L functions in general. And what is interesting is that this is something that Sutherland noticed, that if you take, what you call the dyadic conductor range. So if you take take number n, you take x to x plus x, so sort of a binary, sort of a dyadic range, and you average over all conductors, because you have to average over of a finite number of elliptic curves. So you average over these ones. And then you scale it up and average over the one, and then the murmuration, the curve looks exactly the same. So it's a scale invariant thing. It's a kind of interesting thing, and that's also part of these what Zubrilina and these guys proved for Dirichlet characters. It's kind of interesting. So Sarnak says, he says, this is quite remarkable because BSD could have conjectured this, but they didn't because they didn't do PCA. They didn't have the technology to do PCA to inspire them. I mean, obviously they had the technology to take an average, but unless you do the PCA, you wouldn't think to take this very, very strange average in this way, which is not, I mean, it's not that complicated. It's just like humans obviously missed it for some reason. It's just that it's a curious thing. But apparently, it's a non-trivial thing to do, and AI guided us.
Sorry, there's a question in the chat. Why did you decide to try PCA specifically?
Very good. So basically, we partly did this, as I said earlier. You try everything, including your grandmother's kitchen sink. And what is interesting in all of these things, we couldn't find anything that did less well than 99+%. So we chose PCA because we were hoping to have something interpretable. So that was very human, because PCA is very interpretable, right? Because it's a linear transformation. We're hoping to see something from the transformation. So I mean, it's almost not fair to call PCA an AI algorithm. It's really a stats. It's a data scientific stats algorithm. But I guess it's AI in the sense that, when it becomes in the millions range or hundreds of thousands range, you really need a fairly powerful computer to do it. Yeah, that's why. So in fact, that's a good point. You say, why do we choose the PCA? And the reason we chose the PCA is exactly why it fails the A test. Because, the computer didn't tell us to choose the PCA. We did because we tried everything else and chose the PCA. Yeah. At some point, I hope somewhere, there will be a test that will be something that passes the bridge test completely. So far, we don't know yet, but soon, I hope. So just to wrap up, obviously, so here's a nice things across the centuries, right? So in the 19th century, the eyeballs of Gauss were good enough to make conjectures. In the 20th century, you need some computers, even primitive computers, to make conjectures. In the 20th century, you really need AI to guide our intuition towards conjecture formulation. And in a sense, the future of mathematics is the combination of all of these three different methods. So let me just finish up with this wonderful quote from Harishchandra himself, or you can read it. And I think what he was saying, in a sense, this tension between imagination and intuition versus knowledge and experience is very much pertinent to today's AI-guided mathematical discovery. So thank you very much.
Thank you so much for a wonderful talk. So is Harishchandra saying that it's better not to know too much? That's what he's saying, right?
Yeah, that's what he's saying. That's right.
Okay,
Yeah.
very good. I think this should make all the students happy. The students are always struggling to know everything. And here's someone telling, here are two people, Harishchandra and then Yang, telling you that you should be imaginative without knowing too much.
Well, not me, but the AI.
Right. No, so indeed, it's somehow that's how AI works. But that's also how human beings sometimes work, right? That's what he's saying, that we are not that different from AI in that way, that we try to look for patterns without
That's
knowing
right.
too much, without having too much basic knowledge.
Yeah, sometimes human bias is good and sometimes it's not so good.
Okay.
I think it's
Okay.
I think in some sense that's why the AI guided intuition is very much taking off today, because sometimes it makes you look at things you don't want to look at before because of human bias.
So questions, please. Dr. Katre, you had a question? Or
Yeah, no question, but earlier, the mathematical discoveries which used computer, people had doubt about the proofs, and now the same question may arise for the AI guided proofs.
Yes.
So that is
Yeah.
that is.
So no, that's an interesting comment, because I think it's there is a conceivable pipeline. So in the sense that you can generate mathematical data on the cheap, but data even including sentences, a proof statement, statements, mathematical statements. You throw into the AI, the AI makes a conjecture, and then you have a counter AI which will say, this one is an interesting conjecture. It picks out that one, and then it's going to go through Lean's database, the MATLib, once MATLib is more advanced now, and start to search using a language model for a proof path towards that correct conjecture. I think that this pipeline is clearly being developed by Meta and DeepMind right now as we speak. But I don't know how long it's going to be before this is going to be fully automated. It's going to take a very, very long time. I mean, even typing in mathematics as it goes is going to take a while.
Yeah. So thank you for a very interesting talk. Yeah, it was very nice.
Thank you for listening.
Yeah. Different types of people, they enjoyed the lecture with different backgrounds. I'm
Yeah,
sure.
I was hoping to have people talk and just mix and think what kind of, and give me problems, give me homework. What kind of problems that interest you that could have data that I could run some, or we could run together some kind of pattern detection to raise an interesting conjecture in your favorite field.
Thank you.
Are there other questions? Please unmute yourself and ask if so.
Hello. Hi.
Yeah,
Yeah.
hi.
And you said that like now what I can see is that AI are predicting things like and like we do. So is the basic formalism that our human brains works for also is neural networks, or is it some like what can we say about us basically? I'm asking. Yeah.
Oh, like, are we just essentially neural networks?
Yeah. So
Yeah.
what it is indicating toward? Yeah.
That's a deep question. I don't know. I think that's a question that's I'm not qualified to answer this, but I know somebody who has thought about it. And this is the philosopher Dennett, Dennett, who has been thinking a lot. And you can look on YouTube. He has these wonderful conversations about, are we reducible to neural networks? And I don't know what the punchline. I can't give you the punchline answer to that, but I highly encourage you to look at his. I think it's Anthony Dennett, who's been thinking about this kind of question.
Actually, if I can follow up on that last question, are there people in neuroscience, in biology, who are interested in brain research, who are interested to ask questions like how AI works? Does it guide them to problems in brain, in research on the functioning of the brain? I mean, more than philosophy, directly brain science or neuroscience.
Yeah, absolutely. I can't think of the names, but the neuroscience are definitely. It sounds kind of interesting, because if you take the first neural network that was done in 1956 to 57, what they did was they took a wall of a cadmium sulfide or some photoconducting cell, and they took flashlights and tried to stimulate these photoreceptors. And the only reason these were essentially what I mean, they're neuroscientists. I mean, this is really before the neuroscientists existed. They were trying to imitate the human neuron. That's why it's called the neural network. And they wanted to see by stimulating the neural activation function, can we reproduce, synapses that's like the human neuron, and can it be used for computing? So this is like the first collaboration between computer scientists and neuroscientists before either field really existed.
Yeah,
it's
really.
very advanced. I mean, this is 1957.
The date of that is amazing. Yeah.
Yeah, it is amazing.
Great. Okay, so I don't see any more questions. Or Abhijit, did you have something, a brief question?
Yes, I'll quickly sum it up. I'll rephrase my question. Professor, textual prediction as well as say number series prediction, say for example Fibonacci, or the textual prediction in any of the text editors, it has always been there. Now what exactly has been changed from the mathematical point of view, which actually made AI so advanced? Or we are just repackaging the things and projecting in front of everyone?
So let me try to understand. So you're asking.
So I'll give a quick example. For example, I have a Fibonacci series.
Yes.
In my opinion, it's a classic example of AI, right? We predict how does that number series goes on. I am writing something on my WhatsApp. It gives me a textual prediction. It's a form of AI, but it has always been there from the past. So what has changed from mathematical perspective, which made AI so popular in recent past? Or it is as it is, we are just now leveraging that facility?
I see. No, I think if I understand the question correctly, I think a part of this is large language models, and that really is. I mean, I think in some sense that really is proper AI, in the sense that the large language model has been trained on, in some sense, the entirety of human knowledge. I mean, it has been trained on all of the internet, and because of that, your text prediction that you do in Google when you type Google text prediction, and if you do some of that, even with mathematical syntax, it's more or less correct. So if you take this might be a good example, right? If you try on ChatGPT and you ask ChatGPT to answer some problems in, say, say vector calculus, it will do it fairly well. If you ask it to solve PDEs or ODEs, you will do very well because the syntax has been learned, and in some sense, problems in mathematics that sort of have a routine way of being solved has essentially been learned by large language models. When we, for example, here's something that ChatGPT can do well. Now, here's a question, a problem like in mathematics that it can't do well. So something they can do well is like, I give you a vector field, blah, 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 find its curl. And that, I mean, if you take a first-year undergraduate, the person will say, yeah, but here's how I'm going to do it. I'm going to take the partial derivatives. I'm going to do this, and this is the algorithm by which I'm going to get the answer. And if you type such a problem to ChatGPT, it will do extremely well. On the other hand, if you ask ChatGPT a very, very simple problem, like give me the 15th decimal of 22 divided by 17, it has 1 in 10, 1 in 10 chance of getting it right, simply because there is no shortcut, nor is there any algorithm. If you just on a linguistic level. However, now ChatGPT-4 is clever now. Once it encounters problems such a type, it'll automatically go to Wolfram Alpha and get the right answer and feed that back to you. So that is, again, is linguistics. Once this AI recognizes what type of a problem you're trying to ask, kind of slot it into the kind of answer it should be, and then go into some kind of a solution to this. And I think this is becoming like how we actually do research, right? You encounter some kind of a problem, and you're trying to slot it into, this is likely to be this branch of mathematics, and likely techniques are going to address it, and then you're going to go deep down in this way. But this kind of way of thinking about a problem, I think it really does actually rely on the AI revolution. Yeah. I hope I hope that answers your question.
In detail. Thank you. Thanks a lot for that. Thanks a lot.
Thank you. So there are 2 more questions. I got one on WhatsApp from people watching on YouTube. So the question is regarding AI solving math Olympiad questions. Yes. Apparently, there's a video claiming that it needed considerable human intervention to input the question for AI to input to address properly. So would you like to comment on that? I'm not sure I read it correctly, but yeah, that it needed considerable human intervention.
I see. I as far as I know, what they did is if I understand what they have done is what they did is they trained on all the solution paths of all previous candidates, or standard solutions. And I mean, I guess because this is problems in Euclidean geometry, it's not like I can take my phone and use an app to interpret that. But I think you need to type in the problem, like I give you a triangle of this type and blah, 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 and then show that this length is equal to this. I believe this is okay. But then because it's been large language model trained on all previous solutions, what AlphaGeo would do is we'll find a path like this, but then the output will be human readable.
Mm-hmm.
I think that in some sense that's the breakthrough, and it's gotten to the 80% range. So it will solve it correctly. But of course, I think at some level it has no idea what it's actually doing. It's just building on the experience of previous solutions.
I see.
And what you mean, between AlphaGeo and AlphaGeo 2, it's only 4 months. So I mean, this is really fast, right? The next generation of AlphaGeo 3, God knows what it can do.
When you said no one knows what AI is actually doing, this is actually the text of the last question, which is in the chat window. It says, in what exact sense is AI a black box? Have there been any attempts to break this barrier?
Yeah, so there is actually a very active area of research called interpretable AI. Surprise, surprise. So, which I think uses structures to essentially entangle, try to reduce if it's a deep neural network, for example. That's the worst part of all. PCA and stuff like this are they are interpretable. But once you're into the deep neural network range, where there's thousands of neurons, you have no idea what's been activated anymore. So there's now a systematic field of interpretable neural network research, which is to try to, well, let's try to switch some of this off, and let's try to find exactly which ones are doing what. And so that's very much active. So a good example, and this has been around for a number of years now, like the famous example where a convolutional network's been trained to distinguish between dogs and huskies and wolves or something, and you can do extremely well, and because of this interpretable neural network, this research in this area, they finally pinned down the reason they were able to distinguish huskies from wolves is. It was actually analyzed in the background. If there is snow, it's likely to be a husky. It wasn't at all looking at the dog. But in order to reach that, they were able to pinpoint exactly which region of your neural network is. I mean, this is very much like, like what neuroscientists do, right? How do you know hearing, what is hearing? So now we I think neuroscience is good enough to stimulate, millimeter squared range of your cortex and make you do very specific things. Like, you want to lift up your left arm. You put a probe in here, and you don't lift it up and start doing things with your fingers. So, and this is sort of like this. So this is very much an active research area.
Wonderful. Thank you, Yang, for a very, very inspiring talk. And I look forward to chatting with you about this in the future.
Absolutely. And I hope to see you all in person, either here or in India.
Wonderful, wonderful. We should have you here actually and give us a series of lectures. Let's try to work on that. So so everyone, thank you very much, and we'll end the session here.
Great.
Is that okay, Devendra? All good? Maybe he's not.
Thanks, Professor Ian, for the nice talk.
Yeah, thank you very much. Thank you for having me.
Thank you.
Can you send us the slides of the talk?
Sorry?
Can you send us the slides of the talk?
Yeah, of course. Yeah, no problem. Yeah. In fact, I can probably I can drop it into chat now.
Okay, maybe.
Oh no, I have your email, so I'll just respond to your email. Great. Yeah, perfect.
Okay, yeah. Again,
thanks for sharing the session. Yeah.
Thank you very much. Thanks for having me.
Okay, bye.
Okay. Can end the meeting now. Bye, everyone.
Bye.
Bye.